Welcome to the fifth lecture in a series of lectures by Andrea Montanari as part of the open online probability school, originally designed for the SMS in-person version. He's been giving lectures on mean field methods that as they apply to high dimensional statistics and to non-convex optimization. Last lecture we connected this to the statistical physics models, and today we're going to see a continuation of this. Today we have one lecture, and this will conclude the program for this week. I would just like to give a quick preview of the schedule for next week. Next week, we have a series of lectures by Elhanan Mosel on simplicity and complexity in belief propagation. The lectures will take place on Monday, Tuesday, and Wednesday at this same time. For 1 hour, and on Monday and Tuesday they will be followed by an exercise session, and then we'll also have a series of lectures by Shirishendo Ganguly on large deviations for sparse graphs, and those lectures will take place on Wednesday, Thursday, and Friday. On Wednesday they will take place at in the second part, so what was 17:30 UTC, and then on Thursday and Friday they will take place at this same time. You can see the full schedule on the OOPS website, as well as posting of the slides and videos and exercise sheets and some references for this week's lectures. So without further commentary, just to mention again that the videos are being recorded. In case you do not want to appear in the video, please disable your camera and or microphone. You will have an opportunity to ask questions over the chat, as well as either in the middle of the lecture or at the end of the lectures. You can ask them in person as well. Thank you, Andrea, for joining us again for the fifth and record time so far, I think, in this as the longest running sequence of this school so far. And can we share the screen?
Yeah, share the screen. Okay, so thanks to sticking to the end, for all of you that stick to the end, and thanks for the organization again. And yeah, so today we'll go down to the technical, the outline of the construction of the algorithm for the SK model and generalized p-spin model. So the context is that we want to maximize this Hamiltonian over the hypercube. So this can be either a generalized spin model, so a model which is a sum of kind of multilinear terms, or the SK model as a special case that is just this quadratic Hamiltonian here. Okay, and the coefficient W are given by a geo in metrics. And so for the argument, I'll stick mostly to the SK model until somehow the end, and then I'll change my formula to generalize it, just because the SK model is simpler. So as I anticipated in the last lecture, what we're going to do, we're going to construct an AMP algorithm, and this is going to take this form. So we have a vector ZT in Rn, and I'll index time instead of 1, 2, 2, 3, 4, 5, etc. I'll index time by 0, delta, 2 delta, etc. up to 1, and think of delta as a small constant that then will give me, will reflect in the approximation ratio 1 minus epsilon on the optimization problem. And the way the algorithm will work is that, okay, the general IMP algorithm, at each iteration, I compute a new z at time t plus delta by multiplying the matrix W times a function of z at the previous time, and I subtract this Onsager reaction term. Okay, so what we know in general, so all of our objective is to design the function f and f of t such that this vector z, not really the vector z, really the vector ft of z will give me as good as an approximation as possible to the optimum. And the key thing that we will use, and in fact we'll basically forget about the details of the finite n algorithm for most of the lecture, but the basic lemma that we'll use, that we called before a theorem, is the state evolution lemma that tells me what is the asymptotics of the joint distribution of the vectors generated by this algorithm. Okay, so here on one side, what I have is a function. So I take any psi. So psi can be, so here is a locally Lipschitz function with quadratic growth basically, and I apply this function to the coordinate of the vector z0 up to z1, so there is a constant number of them, just 1 over a delta of them. I take expectation, so this expectation with the hat means just the average over the coordinates, so I invented this notation. And then the limiting probability of this is given by the expectation of the same test function applied to a vector of random variables. And what in this lemma tells me is also what is the joint distribution of these random variables. First of all, the first coordinate is independent of the others, and in fact is normal 0 delta, just you can see immediately by the initialization that is up here. Okay, so here I wrote the initialization, and this will reflect into the fact that z0 delta is obviously normal 0 delta, but all the others are jointly normal with some covariance q. And okay, how do I construct q? Well, q you construct by recursion, okay? So the new q is just the covariance of f. The q s plus delta t plus delta is covariance of fs and ft. Okay, so this lemma really gives me, in a sense, an isometry between, my original vectors that are at finite n, and this instead is Gaussian random variables, right? And so I can now analyze the algorithm by working on this probability space here mostly. Okay, so now I told you in the last lecture, also anticipated that a key ingredient here is to impose some orthogonality condition. So what orthogonality? So I'll define MT to be FT of the previous iterates, okay? And then I want to ensure all sorts of orthogonality condition of the following. So I want the increment so the scalar products of this increment to go to 0 as n goes to infinity. So I want, and this I want it for all s less than t. So increments to be orthogonal with respect to the past, and this again is dictated by somehow the intuition that we have about the structure of low-lying states of this SK model or these spin glasses. And so this is something that probably Eliran Subag talked about in this school. Okay, so how am I gonna do this? Yeah, so let me introduce a piece of notation. Let me call FT. Okay, I will not really use this notation much, but and the sigma algebra generated by Z0 up to ZT. Okay, and okay, so the way I'll impose this orthogonality condition is really something that probably you're familiar with if you studied some probability. Is I'll construct this by, so all these sums over times run over the grids of spacing delta. Where right, so this is the key idea, the key construction, right? So this defines this function. I'll construct these functions f in this way. The function f gives me ft, mt, so I can define the function f or define the sequence of vector mt. And the way I'll construct it as a sum of terms that are the previous increments each time multiplied by something that is measurable with respect to the past. Okay. And now, of course, now if you put this through this state evolution theorem at finite n, it's useful to think of the following two contexts. One that is the finite n space. Therefore, we have three sequences of vectors. We have the the zt that we started with, the us, ut if you want, and ut is measurable, some function that I didn't yet specify of the zt, and then this mt. And then corresponding to this, I will have random variables that are, okay, I'll call, without a lot of imagination, I'll call it capital Z t delta u delta t, and then delta t. Okay, and the relation between these two is that every time I compute empirical averages over these vectors, for large n, they are converged to expectation with respect to these random variables. The way I construct the random variables is I apply the same function that I apply to vectors here, I apply them to the random variable. Okay, so I can now rewrite in terms of this random variable my state evolution lemma. The lemma that I wrote before, I can write it more concisely in the following form. Okay, first of all, let me write the relation between this set of random variable. M delta t will be square root of delta, because this corresponds to M0, plus the sum S between 0 and t minus delta of u delta S, and then Z delta S plus delta minus Z S delta. Okay, so this corresponds, as I said, corresponds to this equation. The finite n equation between the vector is this. And so the way I construct, if you want, this is the definition of the random variable capital M. And of course, what you have is that you have to impose that the random variable u delta S is measurable on the sigma algebra Fs. Okay, so this sigma algebra is whatever is the sigma algebra generated by the random variable z from 0 to S. Okay, so this is my definition of M, and now there is the equation that I brought before for the covariance the z's that I can write. Since mt is my function, I can write the equation for the covariance of the z's that like this. This is given recursively. So again, how do we read these equations? Given all the z up to some time, t, or t minus delta, I can construct up to some time t. I can construct the m up to some time. I assume that somebody tells me how to compute the u's, right? There is some other measurable functions that tells me how to compute the u's. So if somebody gives me all the values of z up to time t, I can compute all the u's up to time t, because by definition, the u's are measurable. Then I use this recursion to compute all the m up to time t. And then to compute the new, to move one step ahead, I use this recursion. Now I know the covariance of the z up to time t plus delta thanks to this recursion. And therefore I can construct all the z up to time t plus delta. And this way I construct the sequence of random variables z0 to z1. Okay. So perhaps I should pause for a second, and ask whether this makes sense, or if there is any question. Please, because otherwise what follows will make no sense whatsoever. Okay. If nobody interrupts me, then so now I came up with this construction. Was I able to ensure this orthogonality property that I was talking about?
Andrea?
Yeah.
Is there a physical meaning to M and U?
Oh, yeah. So if M is really meant to be the magnetization, okay? So again, what is the picture here? The picture that I have in mind, okay, it would be nice to prove more details about the picture, but the picture that I have in mind is that we have this Hamming hypercube, and you have this tree of states. It's not a Hamming, it's the solid cube. And M, at any given time, you are going down the leaf, and MT is the magnetization up to some, when you are at radius t. T corresponds to the radius at which you are. And yeah, so the M vector is the magnetization that you have at that moment. Now, I must say, this is something that I realized in hindsight. I mean, that is not, okay, if you know about physics, this can be useful, but, it's not really necessarily useful for anything in the proof. Okay, so were we able to generate these martingale properties? And the claim is yes, claim this orthogonality, and yes, and claim M delta t for t, let's say, less than 1, and z delta t less than 1. So these are discrete time martingale. Okay, so how do we prove it? So let's go to the proof of this claim. So first of all, a couple of remarks. Claiming that they are martingale is, first of all, is sufficient to prove it for for Z, simply by the way, you know, M is construct, you see that if Z is a martingale, then since U is a measurable, M must be a martingale by this, by the definition above, by the construction above. And second, you know, since Z is Gaussian, it's sufficient to check that that the covariance is the covariance of a martingale, right? So Z delta T, Z delta S is equal to some function that I call Q delta of T minimum with S, and actually I'll call it minus delta shift. Some function of T minimum with S, but for the following I'll call it Q of that function minus delta. Okay, and the you know, obviously the thing goes by induction. Over T, assume true up to T, and let's try to prove the following. And what we want to show is that, so we want to show that E Z delta T plus delta Z delta S plus delta is some function of Q S delta for every S less or equal than T. This is the martingale property. Well, you compute it just. So this is, we don't know. We compute it. So if you substitute the formula for Z, the recursion for Z, then this is the same. You get that this must be the same as the covariance of the M by the second formula. So we use first the second formula and then we substitute M from the first formula. And so you get delta, that is correlation of the first square root of delta. And then you get the sum over T prime less or equal than T minus 1. And S prime less or equal than S minus 1, or S minus delta really. And then the expectation. Okay, let me forget, drop all the superscript delta for the moment. US prime, and then ZS prime plus delta minus Z S prime, U T prime, Z T prime plus delta minus Z T prime. And you see that now you know, only the diagonal terms survive, obviously. And so you get delta plus the sum overall. Let's say S prime less or equal than S minus delta. And then you have the second moment, U S prime square. And now times the expectation, the second moment of the integral of Z, that by induction hypothesis must be Q delta of T prime plus delta minus Q delta of T prime. Okay, so now this is a function only on S, so this concludes the proof of the martingale property. And now give me also a recursion for the Q's, right? Because this is Q delta S, right? So now how do we choose U? Well, I want to choose in such a way that it has second moment equal to 1, so that I simplify this recursion. So I'll choose it. I can always start from any random variable with a finite second moment and make it in second moment 1. So I'll start from any measurable random variable and then normalize it. divided by u bar. Okay, and if you do this, now the recursion for q raised q delta s equal delta plus sum over t between, actually, okay, I don't know, let's say less or equal than s minus delta, and then q delta t plus delta minus q delta t. And this implies that q is actually, and this has to be, okay, if you check the initialization for this recursion, the initialization is q delta 0 equals 0. So together, these two imply what? Imply simply that q delta t is simply equal to t. Okay, so we have now the covariance of this process is very simple. Z is a martingale with covariance t, and how do we construct u? Now, how do you construct this u bar? We'll take a specific choice. I'll construct u bar delta t to be some function, lowercase u, of some other process xt t, and where xt is generated in this way, x delta t will be generated in this way. This is at time t plus delta. I'll take it at time t, and I add v x delta t t times delta plus the change in z. Okay, so this would be my definition of u. Now this defines entirely the algorithm. So here, so defines the algorithm up to two functions, v and u. So these are two functions from reals times the interval 0, 1 to reals. Okay, and okay, they have to satisfy some niceness properties that I will not go into detailing. Okay, so now this up to this function v defines the whole algorithm. I mean, the algorithm, this defines the function that gives u at the next time. So this way define this function ft in the AMP algorithm. Perhaps I'll pause another minute to see if this makes sense now. Here, part of, at least part of the guidance is in trying to, I'm trying to get something that has a well-behaved limit as delta goes to 0. So this kind of difference equation, constructing things to this difference equation is very natural given that. Right? Now, I imagine one could go, even more general and not make the specific choices, but these choices in the end, you get, broad enough to achieve the result that I wanted to achieve. So, and I can prove easily the existence of the limit delta to 0. So they are convenient in that sense. I mean, I could choose things much more generally, but perhaps. Okay, so now one nice thing is that now what we have is that, remember that this q delta t is the covariance of the process z. So E of z delta t, z delta s is q delta t. Perhaps before I wrote maximum minimum with s. So this is t minimum with s. So what does this mean? It means that just z is a Brownian motion sampled at the time, delta to delta.
Andrea, the screen seems to be frozen again a bit.
Oh.
After the definition of u and x.
Yeah, I see. Okay. Interesting. people pause and time to think. So I was saying, yeah. Yeah, so what I said is that Z has this covariance that is equal to T minimum with S. So this means what? It means that Z is just a Brownian motion, a sample that, those times, okay? Now I have to analyze what? Let me rewrite now the two equations that define, this process. I have to analyze X delta T plus delta equal X delta T. Oh, okay, let me not rewrite it. To analyze this first equation, where Z now we know that is a Brownian motion, and the other equation that I have to analyze is the equation for M, that I remind you is M delta T. Now I can write it a little bit more explicitly, square root of delta plus and now there was this variable U that now we wrote it as divided by the second moment. Times, now we know that this is Brownian motion. Okay, so the claim is, okay, this is not, so we have to analyze these two. So it's natural to guess, and it's not too difficult to prove by some kind of stochastic process. So analysis is that as delta goes to 0, xt, all these processes converge to some limit, okay, in the right sense, and this is given by an SDE. I mean, a couple of SDEs, really. One is, of course, V xdt dt plus dbt, and the other is mt. Okay, perhaps I'll take a little bit more space because okay, beautiful. Now, I don't like this having to normalize. So what I can do always is I'll choose the function. I'll impose the constraint that this is equal to 1 for all s. Okay, or equivalently, that, E of mt square is equal to t. Just by Ito's formula, the two things are the same. Okay, and therefore now m simplifies, and it is simply now this gives me okay, so let me now write, actually I'll change things now, switch gear now, and start writing formula for the general. I did the derivation for the SK model. What happens if you do the general p-spin model, where, well, it's more challenging, but you get a very similar formula in the end. except that this function xi second, xi appears in particular. Xi second of S is here, and then there is U S XS, DBS, and xi second also appear in the SDE for X. B, T, XT, DT. So basically the Brownian motion now becomes, you know, always rescale. So now you get so now this gives me at any given time the distribution of my MT. So if I solve this SD, I get a random variable M that tells me what is the distribution basically of the entries of the vector MT in Rn asymptotically. Now how do I come up with an approximate optimizer? Well, I take M1, I'll threshold it. These in general can be, you know, outside +1, -1. So I'll threshold it to get something between -1, and then I'll do some rounding to get a +-1 vector. And now basically M1 is already very close to a +1, -1 vector. This is the estimate of the ground state. And the claim is that, okay, there is a small lemma that one has to prove that says that 1 over n Hn applied to this rounded thing that is a +-1 vector is 1 over n Hn applied to m at times 1 plus small n of 1 with that probability. Okay, so this is okay, not hard. And the other lemma is, okay, now I computed what is the distribution of M. I have still to do some work to compute the distribution of H of M, or the value of H of M. And okay, this can be done. And the claim is that this 1 over n Hn of M equal 1 is equal to, okay, some function of U and V plus molo of 1. And this function is very simple. It depends implicitly on U and V, but is the integral between 0 and 1 of xi second of t e of U t xt dt. Okay, and now, so this is the value. If you give me any set two functions U and V, I give you a linear time algorithm basically that achieves this value, that is obtained by solving the stochastic differential equation and then plug it in this functional. So now what I have to do to design a good algorithm is, of course, there are very bad algorithms here, but what I have to do to construct a good algorithm is to maximize this integral. Okay, so what I want to do is algorithm design is basically the following problem. You want to maximize this functional subject to, well, subject to, you know, the two stochastic differential equation that I brought, and then the two constraints that are E of m squared t equal to t, and then m1. So I said that at the end you do the rounding, and then you do the rounding and so I should have been more precise. This is bigger or equal, and this lemma only holds if m1 is mostly between -1, 1, right? If m1 is very big, of course, the vector m1 is too big, is outside the interval -1, 1, then the thresholding will have a big impact, right? So what you want is that at the end you are in the interval -1, 1. this has to be almost surely. Okay, so now we have to solve this kind of variational problem. Okay, now there are two approaches to this variational problem. One is that you guess U and V and you compute the value. But what's more interesting is really trying to solve it and you know, to see the connection with Parese's formula. And one way to address it is, okay, we relax it. Okay. Second, we construct an upper bound via duality.
You have a question, Andrea?
Yeah.
Does the expectation of MT squared equal to T only for SK or for general mixed p-spin models?
No. No, this we impose for every model.
Okay, thanks.
And you see, this is why I mean, this constraint is crucial. So if you don't impose that condition, then what happens? The constraint Qt equal T, it's difficult to impose, and then it's difficult to get the continuous time limit, right? Yeah. And this is what you should expect, because if you cannot impose that constraint, okay. Perhaps we comment about this at the end. And then, once you have the upper bound, then we move from the dual. Once you have the solution of the dual problem, it's quite easy to find the solution of the primal problem. And mainly, sketch out what are steps 1 and 2. So I'll sketch out these 2 steps, because they really show the connection with, oh, I'm almost done. Okay, notice also that here the only place in which the fact that M is an Ising model, that we are solving an Ising model shows up is in this constraint, right? Is on the endpoint constraint. For instance, one easy exercise is to take, so let's perhaps do the easy one. Okay, one easy exercise is to look at the case in which I impose only the constraint E of M1 square equal to 1. So I don't impose the Ising constraint, but basically the spherical constraint. This infinite M space correspond to the vector M1 having norm square root of n. And okay, in that case, this thing can be solved explicitly. For instance, an easy exercise is to look at this. It's even easier because this is a quadratic problem over the sphere. And you can check that in this case, this problem gives a value. The value of this optimization problem is 1, which is 1/2 of the leading eigenvalue of the GOE matrix. Okay, so how do we do the relaxation? So step 1, the relaxation. Well, instead I have a specific way to construct U and V, but now I replace U by any measurable function on the sigma algebra Ft, where Ft is the sigma algebra of the Brownian motion. So I optimize over a larger space, and over this space, of course, again, what I have to do is I have to maximize and then Okay, so you have basically, so the picture is that we have time, we have m, and we have time is between 0 and 1. This has to end up between +1, -1 at the end, and at each time the constraint is, so I kind of can design the diffusion coefficient to be measurable in such a way that at each time m is in the, m as second moment equal to t, and you end up in the interval -1, 1. And all the time I have to maximize this thing, right? Now, the real constraint that causes, of course, make the problem challenging is, one constraint that make the problem challenging is this one, because there is, of course, infinitely many of them, really. So what we do is that we write a Lagrangian. Okay, one way to write the Lagrangian is that, I take any function from 0, 1 to reals non-negative, and then I define u of t to be the integral between t and 1 and so now I called gamma this in the same way as I called the order parameter in the Parisi formula, not by chance, but because it will end up being the same. And then I define J gamma, that is the supremum over all, adapted processes U of, and then I have okay. Now I claim, and so, okay, sorry, the supremo is subject to the endpoint condition. This endpoint is always almost sure. Okay, so now this is very nice because this, of course, gives me an upper bound on the relaxation, right? And basically what happens is that, okay, so I added the constraint as a Lagrange term. It's a bit different. So when the constraint is satisfied, the claim is that this term here vanishes. Okay. So this term here vanishes when the constraint is satisfied. And yeah, okay, perhaps I'll check that. So the term there is the expectation of the integral between 0 and 1 of nu t times psi second of t u squared t minus 1 dt. And by the way I wrote things, this is the same as the expectation of the integral between 0 and 1. And then there is another integral between 0 and 1. And then of psi second. Now I'm rewriting, remember that nu is the integral of psi second times gamma. And now there is, this piece psi second of t times ut squared minus 1. And then there is, here there is a ds, there is a dt. And here the integral defining nu, I integrated s between t and 1. So I put an integral between an indicator function of S bigger than T. But you see that now if you use Fubini, you invert this to 2 integral, I get here exactly, I get the integral between 0 and 1. So I want to do in ds. And then there will be xi second of S, gamma of S. And then when I do the integral over T, I get the expectation of M of S square minus S. This is when you integrate over T. Okay, and so this is 0 if the constraint is verified. So because of that, on the constraint, this is 0, so you get a relaxation. Okay, and so now the point is, I want just to compute a J gamma. How do I compute a J gamma? Well, you do dynamic programming. So namely, you write some J gamma of TZ, which is the sup. So this is the optimum when I do the value of this optimization problem when I start with stochastic optimal control problem, where the particle, basically the particle MT. So the picture is here, M at time T is a position set, okay? And then I have to optimize between T and 1. So this is the sup over all controls that are adapted between T and 1, and then of the same basically objective, except that I go only between T and 1. Then there is xi prime of S US plus 1/2 mu S xi second of S U square of S minus 1 d S. And this is always with the constraint. Now the constraint has to be, since I start at Z, the constraint has to be that Z plus the integral between T and 1 of xi second of S US dBs is in minus 1, 1. Okay, so now you have this quantity, and now you write a dynamic programming equation that gives you this in terms of sum. So I'll stop writing details, but in terms of J at time, some bigger time theta and some other position, I don't know why. Okay. And the control for some theta bigger than T. And now, once you have a dynamic programming equation, at least formally, you can take the limit theta to T, and you get a Hamilton-Jacobi equation. Hamilton-Jacobi-Bergman equation. So a PD for parabolic PD for J. Okay, so this parabolic PD allows me to compute J gamma. And okay, the connection with the original thing is, of course, that J gamma is equal to J gamma of 0, 0, the original upper bound. So you get a PD for this functional J gamma, and the value of the relaxation is less or equal than J gamma 0, 0. Okay, now how is this related to the Parisi PD? Well, basically what happens is that up to a change, up to a small constant, basically, if you, instead of working with J gamma, you can work with the Legendre differential dual of J gamma, namely phi gamma T X is, okay, now I don't remember it, but there is J gamma T Z, and then there is something like minus Z times X, and this is probably is mean over Z. And then there is some constants that some other factor here to eliminate terms that are not interesting that I don't remember. But basically, once you do this transformation, then you can check that this phi satisfies. Okay. So now this gives you and the corresponding relaxation. Now you get by doing this transformation, you get that the relaxation is less or equal than P of gamma. Okay, and you can carry out all of this program as long as gamma is in this space. At least it was carried out as long as gamma is in this space L gamma, and therefore you can stick here an inf. And at the end of the day, you can verify that if the inf is achieved, you can reverse all the step and come up if inf achieved at gamma star. You can reverse all the steps of these proofs and come up with the two coefficients that we wanted, v tx and utx, that are actually derivatives of this function phi. Yeah, so this in a sense, at least to me, it clarifies a little bit the mystery of this Parisi's formula, in which you start with a maximization problem and the value is given in terms of the minimization problem. And at least now in my mind, the way I understand it is that you have a maximization problem, you have an algorithm that solves that maximization problem that is described by a stochastic process, and you maximize the stochastic problem, you get the value that the algorithm achieves, and really the Parisi formula is the dual of that problem. Okay, in the end, of course, as we talked about in last lecture, you get the Parisi formula, except that on a different variational space that doesn't have anymore the non-decreasing constraint, so you get different value, and this coincides on the optimum only under the normal overlap gap condition. Okay, I guess that's all. Thank you. And thanks again to the organizers of this and to everybody that stick around.
Thank you, Andrea. I will unmute all the participants so we can all thank him together.